Hello everyone and welcome back. Before we begin, I just wanted to mention that this video is going to be a direct continuation of my last video on universal gravitational force. So if you have yet to see it, I highly recommend that you watch that video first before watching this one. It should be just before this video in the playlist. Alright, so I want to make use of this last problem to show you one more thing. If we had a physics question where you were asked, I drop an object from a certain height, how much time does it take to hit the ground? Well, you would use our gravitational constant on the surface of the Earth, which is 9.8 newtons per kilogram, which using Newton's second law would also come to 9.8 meters per second squared downward. So there's something I want to show you involving the universal gravitational relationship. Let's say I have a mass I'll simply call mass x, and that mass is raised in the air on top of a building and is being dropped toward the surface of the Earth. I want to find the acceleration of this object as it falls. The only force on it is force Earth, only I'm not going to use our relationship of 9.8 newtons per kilogram. I'm literally going to use this. So we have Fg, which is going to be the only force in the object, over mx, the mass of the object. Fg is this relationship. So I have g, mass of the Earth, mass of the object, over radius squared, because it's in the relationship, divided by mx. And what happens? These two masses cancel, and I end up with this. So what happens if we do that? I have g, mass of the Earth, divided by the radius of the Earth squared, and I will get 9.8 newtons per kilogram. Because meters squared, they cancel. I have 1 kilogram and not 2, so only one of these kilograms cancel. I have this unit left, which again translates to an acceleration of 9.8 meters per second squared, and these are both downward. This means that we can find the acceleration of free fall on any planet in the solar system, as well as the force on an object if we know its mass. So to sum up, this relationship will find you the gravitational force between any two objects with mass. If it is an object on a planet, mass 1 is the planet, mass 2 is the object, and you will find the weight of that object on that planet. If I go through second law, acceleration is F net over mass. That's the mass of the object you're targeting, which is mass 2, which means the acceleration due to gravitational pull on any planet will be solved by g, the mass of the planet, divided by the radius of the planet squared. That's how we just solved for the 9.8 meters per second squared on Earth that you are familiar with, but this relationship can be used for any planet in which you know the mass and radius of the planet. And side note, you could find this force and acceleration at any distance. It doesn't have to be on the planet's surface. So if they give you this radius of the planet, but then they tell you this space station is a certain height above the surface of the planet, the distance you will actually use for the equation is the combination of both, the radius of the planet plus the height. This is actually a pretty common question to see if you actually know what the distance you're going to use in the equation is. All right, I wanted to make this video for the specific relationship, so I will end it here. Have a good day. This is Mr. M signing off.